So I just gave Tomislav some hints as to how to make some steps forward in his encoding, but I'm actually going to move on to talk about the heart of the issue, right? So first, let me review. So how many people here know how the three colorability is used to do the zero knowledge protocol?
I watched the video, so I have a general understanding of that, how it can be done. I have to watch it 3 or 4 more times to actually be able to explain it to someone, but
Okay, well
I'm
let's
halfway there.
just go over it. So ignore all the row stuff. And let's say we have some graph, and I'm going to assign. I want to prove that I can do a three colorability of the graph. Now, I haven't checked this particular graph. Let's see if that's possible. So let's make this one red. That means this one has to be either green or blue. So let's pick green. And now let's pick green again here. If I pick blue here, then that's a three coloring. Do you agree?
But on the left and right bottom,
Oh,
green.
you're absolutely right. Okay, so if I pick blue here, yeah, it's not three colorable, is it?
Mm.
This one's not three colorable. So in order to make a graph that's three colorable, imagine that I've gotten rid of this link. Okay.
Mm-hmm.
All right.
And coloring graphs and maps is basically the same, right? Just
yeah, that's right. Just the countries become nodes and borders become edges.
And I wanted to ask you, you removed one line, or you could like add more dots, right?
I could add another node in between. Yeah.
I'm interested, maybe not now, but you know, what does it mean to add or subtract something to make it tree coloring from perspective of proofs? But
Yeah,
maybe this is for another time.
that's an interesting question. Okay, so we remove this edge, and so if I do red, green, green, blue, then that works. Okay, so now the verifier doesn't know the colors, right? So we're going to cover up the colors, and that covering up is a cryptographic operation, right? So we make a commitment to those colors. And then the verifier gets to select an edge and say, all right, show me the colors of the source and the target of that edge, or either end of that edge. And basically, if they're the same, then the verifier knows that the prover was cheating. If they're not the same, the verifier has some confidence, but not, but you know, maybe there's some other part of the graph where there is a conflict. So, but the next, so what they can do is repeat, but in the next round, what the prover does is it applies a permutation randomly. So it randomly picks one of the 6 permutations and recolors according to that permutation. So if I change blue for red, for example, so this becomes blue, green, green, red, right? Now the verifier picks another edge and again asks, you know, the colors of the source and the target. And if they're the same, then the verifier says you're cheating. Otherwise, the verifier says, oh, I've got a little bit more confidence. So they can go around this loop over and over and over again until the verifier is certain that the prover, you know, within some degree of certainty that the verifier is comfortable with, that the prover isn't cheating. Does that make sense?
Yes, this is a interactive part, right?
Yeah, it's an interactive part. So just for fun, I want to show how you can code up that basic interactive protocol directly in Rho. Okay? And I'm not going to focus too much on the dialogue between the prover and the verifier because that's very straightforward. I'll talk a little bit about it. But let's just imagine, what does it mean to actually represent the graph? Now, there are a couple of different ways we could do this. We could use toggle, which is that theory of graphs, and then encode toggle into Rho. But I'm just gonna, for now, encode graphs directly into Rho. And then you can see for yourself how this relates to the toggle encoding. You'll find that they're very, very close. And without loss of generality, I'm going to assume that the graph is directed. Now, we can always get an undirected graph out of a directed one, and I can always get a directed graph out of an undirected one. So I'm not particularly concerned about that if you go look up the graph theory. But what that means is that for every edge, so I'm going to think of a graph as having some nodes and some edges. And since the graph is directed, for every edge, I can ask for its source, which will give me a node, and I can ask for its target, which will give me a node. Is that clear? Is everyone happy with that?
Yes.
Okay, wonderful. So now I'm going to give a translation. So if I have a graph, it's going to be parametric in some channel A. We don't know what that name is, but it's a parameter. And we're going to ask from that channel for the list of edges. So I've used bold to indicate that this is a vector. And we'll see an example in a minute. But think of this as some long list that we're going to destructure the value coming out of A. And now we're going to do a big parallel composition where we translate the nodes given G. Right, so we turn the translation of the graphs into the translation of the nodes. Basically, it's a big parallel composition of the translation of each node. So what is the translation of a node given G? Well, for each edge in which the node is a target, we're going to call repeater. So this E is free in this expression, but it's going to be bound here. So there's going to be some E in the edges, which we're supplying through A, which is binding this E. So then it's, it's just up to whoever's doing the input on A to make sure that the E's mentioned here line up with the channels for the E's that we want to refer to that particular edge. So when it's a target, we're going to do a little repeater process, and I'll get to that in a moment. If it's a source, we're just going to make a fresh K and send it down that edge channel. And then a repeater, all it does is along the edge, it listens for a value and then outputs the value that it got and goes back to being a repeater. Now, the reason we do this recursion this way is because we'd like the graph to be stable. So what is the graph actually doing? What the graph, the real graph is the graph of rewrites. So when I have an edge in the graph, it's going to be because I have a rewrite between someone that is sending and someone that is receiving. A process that's sending and a process that's receiving. Now, after such a rewrite, the question is, do I get back to my original graph? Here, we will get back to the original graph. Why? Well, if there's an E that's sending over here, then we'll so there's an E between some source and some target, and so the source of this edge is going to send along E. So this repeater will pick it up and put it back. So the source, there's some source over here for some other node, that was depleted by one of the outputs, but we're going to put it back. And since par is commutative, right, this will just shuffle around, and it will now be back in the source part of the node that was sending over here. And since this thing was taken away, we need to put it back. So this will be put back, and so now we have we'll get back to our original graph after that communication. Does that make sense?
So can we imagine that we are somehow traveling through the graph and like pulling apart and then assembling it back?
Pretty much, yeah, that's right.
Because I look this repeater as a path, but it's not like a path, right? It's just moving to the graph.
That's right. That's one way to think about it. Okay. So let's do an example.
That was an infinite loop, right?
Yeah, it's in an infinite loop. So so if it weren't infinite, then the graph would fall into dust. Right. The point is we want the graph to be stable. So the first thing is that after you do the input output, you need to get back to your original state. If you don't get back to your original state, you've moved to a different graph. And so if you move to a state that stops, then your graph disappears. So the graph is in the doing. Its being is the doing. Okie dokie. So here's an example. So let's imagine that. So I'm going to label everything just to keep our head straight. Okay, so the nodes are P, Q, R, and S, and the edges are X, Y, Z, U, V, and W. Is that clear?
You said we don't have Z.
No. That was just for 3-color ability.
Oh, okay.
Right. For this graph, I put the edge back.
Okay.
So the graph we have in hand is not 3-colorable as near as I can tell. Okay. All right. So now let's follow the formula. So G of A, I'm going to get my edge list from this, U, V, W, X, Y, Z. So that's all listed here. I'm going to pull those out of A. So I'm destructuring, and now I have variable binders that are scoping all of these things. Does that make sense?
Yes.
Okay, cool. All right, so now let's look at the translation of P. So P given G is going to be, well, let's look at P. It's got one incoming edge, that's X. So it's going to be a repeater on X, and it's just going to do an output on U and Y. See?
Yeah.
Yep.
And then over here, we go over Q, one input, that's Y, so repeater on Y, and do an output on V and Z. And over here, we do a repeater on Z and an output on W and X. I should flip these around just to be consistent. And since I used K before, I'll use K everywhere. Oops. Sorry about that. Okay, so that's cleaned up. And then S is just going to be, so all of them are incoming. So S is a sync, right? So it's a repeater on U, V, and W. And there's our graph. So you just plug these directly into here, and that's the expression for G. So far, so good, yes?
Yes.
Okay, all right. So now let's talk about coloring. Okay, so our colors, in this case, we're only talking about 3 colorings, so I'll just use the numbers 1, 2, and 3. And the reason I'm choosing numbers is because, you know, I can give a church numeral encoding of those as processes if people are pedantic and stickler that I have to make sure I've got an encoding of whatever I'm sending, right? Okay, so then a coloring is going to use a trick. And the trick is for every node, for the translation of every node, I can take its name, right? So here's a process, so I can take the name of it. Here's a process, so I can take the name of it, and so on and so forth, right? So now the coloring of G is just going to be G in parallel with on the name of a node, send the color. Whatever your coloring C of N is, just send that color on the name of the node. And guess what? We're guaranteed that these nodes, the nodes will be distinct. The names of the nodes will be distinct. Why is that? As long as you're careful to send distinct name for each of the edges, you're guaranteed that the names of the nodes will be distinct. If 2 nodes are distinct, their names will be distinct. Why is that?
Because we are generating new names for each.
No, remember the name of the node is going to be the quote of this process.
I mean, for each node, the generated process must be different because we're specifying input and output edges.
That's correct. That's right. If a node has exactly the same, if 2 nodes have exactly the same input and output edges, unless you have a multi graph where you can have 2 edges between the same nodes, they're designed to be distinct. But here we're assuming that you've only ever got 1 edge between 2 nodes. That's the key property that we're using. Does that make sense?
Yes.
Yeah.
Yes.
Okay.
Cool.
Cool. All right. So those are guaranteed to be distinct. So now our verifier, the core of the verifier is quite simple, right? The verifier is going to do a join, and it's going to listen on the source of an edge, at the name of the source of an edge, and at the name of, target of an edge and the source of an edge, right? So it picks an edge randomly. It then does a join, getting the 2 colors. And then, so here is, you say what edge you're going to use, and you say where you're going to send the result. So here down the answer channel, we're going to send not C1 equal C2, right? So if the colors are the same, then this will be false. So the verifier rejects the coloring. If otherwise, the verifier accepts the coloring. So then an amplifier has got to do a couple of things. Well, first of all, along here, at this step, it needs to randomize the edge choice, right? So we need some, it shouldn't be E, but in fact, it should be pick a random E. And the other thing we need to do is, if we're going to, so what this does is it just loops, right? Along some R, which is the number of repeats, we pick it, we look for an N. If the N is 0, we stop. Otherwise, we do the verifier. We output basically N minus 1, and then we recurse. All right. And so here, what we really need to do is to randomly pick the edge, right? And the other thing we need to do is to tell the graph we're repeating the protocol so it can apply a permutation to the coloring. And that's not particularly hard. I leave that as an exercise. But you get the point, right? You understand what we have to, so here you have to you have to guard this whole thing with a signal, waiting on a signal. When you get the signal, you apply a permutation. So you randomly choose a number, and that number gives you a permutation, which you then apply consistently all throughout here. So here, when we're about to recurse, we also have to tell the graph to redo the thing before we launch the core of the verifier. So that's it. Does that make sense?
Yes. And when we ask for permutations of edges, we basically we can be completely sure we can execute this on all edges, like complete. We can investigate complete graph, verify complete graph.
Yeah, but if you have
want.
if you want, you could do that. But notice that each time you're getting a randomized version of the coloring. Each time you ask for another edge, you get a randomized coloring. So you don't know what the colors are. Right. Well,
I'm curious how we can be sure if we are basically verifying only part of it. How this is good enough?
No. You do. It's probabilistic proof checking, right? So
why is this good enough?
So you only do you can iterate the process. So like think about it just in the binary case, right? So you've got some colorblind person and you've got two pins, a red pin and a blue pin. So the colorblind person needs to verify that you can actually see the colors. So what you do is you give the pins to the colorblind person and you say, okay, now you can either swap them or leave them the same. Do whatever you want and then bring them back out in front and I'll tell you which one is red and which one is blue. So the first time I have a 50-50 chance, right? So I could be bluffing. So let's repeat the process. So now the next time I have 50-50 times 50-50 or 1/4. And the next time I have 1/8 and so on and so forth, right? So we can make the iteration of the process get down to a level of chance that the verifier is willing to accept. Does that make sense?
This makes sense. Yes.
And so it's the same thing here. We can make it so that, we can repeat this as many times until the chance that I was bluffing gets, as small as we want.
Yeah, makes sense.
Cool. All right. So this is where I want to leave it today. Go ahead.
So I have one more question. So you said each time we are asking, we need to change the coloring.
That's right.
And this is like interaction, but we can somehow do this without interaction.
You can turn this into a non-interactive protocol. That's correct. I'm not. I haven't talked about that yet. We can talk about that next time. But the main point I wanted to get across is, in one page we did the graph encoding, and in one line we did the coloring, and in one line we did the core of the verifier. This is why the the row calculus is incredibly expressive. I mean, even if you fill in all the details, you don't get a much bigger spec. This is a teeny tiny encoding. And, I argue that it's incredibly intuitive. There's nothing here that's genuinely surprising.
Yeah, definitely.
The only tricky part is the name using the process, the translation to of the node, the name of the process that translates the node is the way to do the commitment, right? So this is the commitment part that is unique or interesting, right? It uses a feature of row that is unique to row. So, but apart from that, everything else is super intuitive.
I think that when, you know, one day we are like doing everything in rolling, we will never look back.
I don't know about that, but I thought this is super enlightening. You know, it's like it only takes a few minutes to write this down, and you can see how expressive the language is. Great. Well, again, keep plugging away. Don't give up. You know, just all you have to do is to find a way to recurse on data. The trick is, how do I, since I can turn data into code, what I'm interested in is how to suspend. I want to make a recursive data structure. So a recursive data structure is going to be the same as a recursive process with a little bit of quoting. That's the idea.
Okay, I will definitely play more. Yeah.
Cool.
I want to understand this completely, so
cool.
I will definitely not give up.
Good. Very good. All right. Thank you all. I appreciate your time. Any questions? All right. Well, stay safe, and we'll see many of you in Dev Stand Up in a few minutes.
Great. Thanks again, Greg.
Thanks.
Cheers.
Bye-bye.